Welcome to lecture number 8, an online, the NPTEL online certification course on bioreactors. When we finished up the last lecture, we had looked at a problem on enzyme inhibition. Before that, in the lecture itself, we had looked at three types of inhibitions: the competitive inhibition, the non-competitive inhibition, and the uncompetitive inhibition, which were different in the way the inhibitor affects the reaction. In the first case, the inhibitor bound to the enzyme. In the second case, the inhibitor bound to the enzyme substrate complex, and in the third case, it bound to both. I think I mixed up the last two, but you get the idea. Where the inhibitor binds made the difference. And then we looked at a problem which could help us understand this a little better. Let us work out that problem in this lecture. Practice problem 2.2. An enzyme normally displays Michaelis-Menten behavior in converting a substrate S to a product P. It gave the following data when its Michaelis-Menten parameters for the above conversion were estimated in the presence of another substance I at different concentration. Determine the type of inhibition and the inhibition constant. The Michaelis-Menten parameters Vm and Km at different inhibitor concentrations were given in this table. Now, how do we go about it? Let's ask our regular questions. What is needed? The type of inhibition and the inhibition constant, Ki. What is known or given? The data on the Michaelis-Menten parameters Vm and Km at different inhibitor concentrations are given. And how to connect what is needed to what is given? We have seen that Vm and Km change differently with I for different types of inhibitions. I myself got a little confused, but that's okay. With practice, you should be fine. For the competitive inhibition, V equals Vms by Km into 1 plus I by Ki plus S. The Km gets modified. For the non-competitive inhibition, the Vm gets modified. And for the uncompetitive inhibition, both Vm and Km got modified in this fashion. This is a summary. The type of inhibition is competitive, non-competitive, uncompetitive. In the case of competitive inhibition, Vm remains the same, there is no change, whereas Km changes. In the case of non-competitive, Vm changes, but Km does not change. And in uncompetitive, both Vm and Km change. So we need to find out what changes here. Now, if we look at the data, if we inspect the data, it tells us that Vm does not change with I, but Km changes. Let me show this to you here. The data was this. As the inhibitor concentration changed 0.5, 5 and 10, the Vmax remained the same at 0.33, right? Whereas Km changed. Okay, this is what we saw, what we said earlier, and this is what the data shows us. So, this is clearly a case of competitive inhibition. So, that is straightforward. So, that is the first question, what kind of a competition it is. So, for competitive inhibition, this Km dash, the new Km, is Km times 1 plus I by Ki, right? And Km dash is Km by Ki into I plus Km. I have written it of a form of y equals mx plus c. Remember, we are dealing with a set of data here. Therefore, whenever we deal with data, we need to use the entire set of data. If you just pick points from there, the errors in the data collection would directly get transferred and probably get magnified. If you're using the data point which happened to be incorrect, then the errors would be large in the estimates. That's the reason why we need to use the entire set of data whenever we have data to work with. And we are trying to use the entire set of data to find whatever is necessary here, which is the inhibition constant. To do that, I'm looking at this in a y equals mx plus c form. Km dash is y, I is x, and the slope in that case is km by ki, and the intercept is km. We have data of Vm, Km with varying i's. So I is the independent x coordinate, Km dash, the modified Km, is the y coordinate. If we plot it that way, then we could get Km, Ki from here and Km from the intercept. This is what we just mentioned. It's good to repeat this. When we have a set of data, it's best to use all the relevant ones. If we plot Km dash versus I, we would get the slope as Km by Ki, and thus we could find Ki. Let me show you the working as a spreadsheet. I have I here and Km dash from the table given here. This is for plotting. When I plotted this, I got Km dash versus I as this. The equation was y equals 0.012x plus 0.12. Y in this case is Km dash, x is I, so Km dash is 0.012I plus 0.12. That is what is shown here in this graph, the same graph copy pasted Km dash versus I. So the slope Km by Ki is 0.012, and therefore Ki is nothing but Km by 0.012 from here. We also know, and that is Km we know from the intercept to be 0.12. So 0.12 by 0.012 is 10. So the inhibitor constant happens to be 10 millimolar. Right? I think that is good enough for this lecture. That covered the practice problem. Let us meet in the next lecture to take module 2 forward. See you then.